Imagine putting $1 in a magical bank account. The bank promises 100% interest after 1 year, so you expect $2. But then the bank asks a strange question. What if it adds part of the interest earlier, and that new money also starts earning interest? Split the year into more and more tiny moments, and your final balance creeps upward. It does not grow forever. It approaches a very specific number, about 2.718. That number is E, called Euler's number. But E is much more than a bank account trick. It is the natural number of continuous change. In this video, we will build it from pictures, not memorization. Start with $1 and one growth step. A 100% increase gives 1 times 2, which is 2. Now split the same total rate into 2 steps. Each step grows by 50%. 1 becomes 1.5, then 1.5 times 1.5, which is 2.25. With 4 steps, each step adds 25%. The result is 1.25 to the 4th power, about 2.44. 12 monthly steps give about 2.61. 365 daily steps give about 2.715. Every time we split the year, each jump becomes smaller, but there are more jumps. The balance rises quickly at first, then begins to settle. The battle between smaller jumps and more jumps is exactly where E lives. For n equal steps, each step grows by 1 over n, and we apply that growth n times. So the final amount is 1 plus 1 over n, all raised to the n. As n moves toward infinity, the staircase becomes almost smooth. The values squeeze toward 2.71828, and the remaining digits continue forever. This limit is one clean definition of E. Infinity here is not a giant number we eventually reach, it is a direction. Keep making the steps finer, and watch what the result approaches. Continuous growth is the smooth curve hiding inside infinitely fine compounding. There is an even deeper picture. Suppose a population grows at a rate equal to its current size. When the population is small, it grows slowly. When it is large, it grows quickly. On a graph, growth rate means slope. So we want a curve whose slope at every point equals its own height. Start at height 1. Near the beginning, the slope is 1. A little later, the curve is higher, so the slope must be steeper. Higher again means steeper again. This feedback creates the exponential curve y equals e to the x. At x equals 0, its height is 1. At x equals 1, its height is e. Most functions change shape when differentiated. This one does not. The derivative of e to the x is still e to the x. That is why e is the natural base whenever the amount of change depends on the amount already present. Turn the growth rate positive, and you get compounding money, reproducing cells, or an early-stage population. Turn the rate negative, and the same curve describes cooling, radioactive decay, or medicine leaving the bloodstream. The general pattern is e raised to k times t. The constant k chooses how fast the process runs and whether it rises or falls. A useful time marker appears when k is negative. After one natural time unit, the amount is multiplied by 1 over e, about 37%, so e is not a mysterious decoration in formulas. It is the conversion rule between a local instruction, change in proportion to what exists now, and the full story across time. Now look at a completely different picture. The curve y equals 1 over x. Measure the area under it starting at x equals 1. As the right edge moves, the area grows. The special point where the accumulated area becomes exactly 1 is x equals e. This gives another definition. The integral from 1 to e of 1 over x is 1. Why does this connect to growth? Because equal areas under 1 over x correspond to equal multiplication factors along the x-axis. Moving from 1 to e adds 1 unit of area. Moving from e to e squared adds 1 more. Area turns multiplication into addition. That area is the natural logarithm, and e is its natural unit. The growth picture and the area picture are two views of the same structure. There is one more surprising doorway. On the ordinary number line, e to the x describes smooth growth. On the complex plane, multiplying the exponent by the imaginary unit turns that growth into rotation. Euler's formula says e to the I theta equals cosine theta plus I sine theta. As theta increases, the point travels around the unit circle. Put in pi, which means half a turn, and the point lands at -1. So e to the I pi equals -1, or e to the I pi plus 1 equals 0. Growth, rotation, pi, 1, and 0 meet in a single line, not by coincidence, but because continuous change follows the same exponential engine in different directions. This is why E keeps appearing in science and statistics. Random independent effects often combine by multiplication, while logarithms turn those products into sums. Smooth growth and decay create exponentials. The bell curve uses E to make probabilities fade smoothly away from the center. Waiting time models use E because the chance of an event can depend only on the present moment, not on how long we have already waited. Whenever tiny proportional changes accumulate, or multiplication needs to become addition, E is nearby. You do not need to calculate all of these examples today. The important skill is recognizing the pattern that summons the number. So, what is Euler's number? Remember 3 pictures. First, finer and finer compounding approaches E, about 2.718. Second, e to the x is the unique curve whose slope equals its height. Third, the area under 1 over x from 1 to e is exactly 1. These are not unrelated facts. They are 3 windows onto continuous proportional change. If pi is the natural number of circles, e is the natural number of growth. You may forget the digits, and you may forget the formulas. Keep the pictures, and the formulas can be rebuilt.